friction may seem like an easy enough topic, but we are going to do way more than just saying if you rub your hands together, the heat that you feel is due to friction. That's what you may have learned in middle school or something. What we really want to do here is be able to come up with an equation that will predict how much friction there actually is. And once we have how much force there is, boy, we can predict what's the acceleration going to be, how fast it's going to be going after a period of time. There's a whole new world that it opens up for us. So imagine if we had this crate sitting on our driveway and we pull it with a rope. It's not going to move completely freely. There's going to be friction there. So as I pull on the rope to the left, friction is going to oppose that motion. And that's one of the important things about knowing about friction. It always opposes the direction of the motion. So it's trying to be pulled to the left, so friction will be pulled back to the right. All right, let's just see if we can identify some of the variables that would change how much friction there would be. We have to understand what friction is. And if we get into a microscopic view of both surfaces, the wood and the concrete have microscopic irregularities. There's peaks, there's valleys, and they kind of nest into each other as they sit against each other. And they don't slide freely because one peak is bumping against the valley of the other. All right, so that's what causes the friction, but let's see what would create more friction. What would happen if I put a whole bunch of weight on there? Aren't those peaks and valleys going to be pressed into each other with more force, and they're not going to be able to lift off of each other and move past? So more weight, that's the force of gravity we call weight. More weight is going to hold those things together, and you'll get more friction. Now this would not be an equilibrium here. It would not be accelerating left or right, but as my picture is shown, it would be accelerating down because that was the only force down. So it's not accelerating into the ground, so there must have been the ground pushing back up. And that's going to be an important variable that we need to identify. That if gravity is pulling the thing in or down, the surface is pushing back up perpendicular to the surface. We call that the normal force. And normal is just a fancy word for perpendicular. When you were in middle school, you learned that two things were at right angles to each other. Then you learned a bigger word called perpendicular. Now we're just making up another word, and it's called normal. When you get to college, you'll learn if two vectors are at right angles to each other, we call them orthogonal. But it's all the same thing, just at right angles or perpendicular to. So and it is important is that gravity's pulling down on this right here, and the surface was pushing back equally, but these two things aren't always going to be equal to each other. All right, so one thing that affects how much friction we get is the normal force, and that's simply how hard the two surfaces are pressed against each other. Another variable that can affect it is what surfaces there are. If this was a microscopic view of wood against concrete, you can see the peaks and valleys are very, very large and very rough, so they're going to grab hold of each other. Ice here is probably a lot smoother, or maybe the crystals break off, so there aren't that many peaks and valleys to begin with. So no surprise, it's going to be a lot easier to move that across ice than it would be your driveway, but it has to do with the surface irregularities and the size of the peaks and valleys. And then we have two different kinds of friction. So when the pallet here is just sitting against the driveway, the peaks and valleys can nest into each other, and they don't want to slide past each other, and that is called static friction. Static is unchanging, or in this case, not moving. If the two surfaces are actually sliding across each other, that's changing in movement, so we call that kinetic friction. So if that pallet were sliding over that, it has to actually lift up so that it can get over the peaks and valleys. And the peaks and valleys don't nest into each other quite as deeply because they're sliding over the top of each other. So with static friction, you're going to be able to get more friction when it's stationary, but when it's sliding like this, it's kind of more grazing over the top and not nesting deep into the two surfaces. So you don't get as much friction when it's sliding. We call it kinetic friction. So just to kind of formalize these two things, static friction is the force which must be overcome to get it moving, to initiate movement. And kinetic friction is once it is moving, that's the force that must be maintained, or it must be overcome to maintain this movement. So if I have a block of wood sitting on a table, got a little weight on it to press the wood into the surface so we can measure the forces. I have a string here, and I'm going to pull with variable amount of force on that. And we want to see what the friction does. So with Newton's second law down here, remember that if the force is zero, if the net force is zero, the acceleration will also be zero. So watch what happens as I pull on this string. Pull more and more here, friction gets more and more and more, until it breaks free, and now it starts to slide. So that's an important thing as well, is that when we had static, if we pulled a little bit, friction pulled back equally, so that the net force was zero and it didn't accelerate. And the harder, I'll play that again, the harder and harder I pull on the string, the more and more friction there becomes. But there's a limit to how much friction I can get before it just can't hold back anymore and it breaks free and it starts to move. But when it broke free, friction, this is kinetic friction now, dropped down to a smaller amount so that there was more force that way than there was that way. A net force would cause an acceleration. Let's look at it like this. So if I measure how hard I'm pulling, so if I pull with 2 newtons and it doesn't go anywhere, the net force must have been zero because it wasn't accelerating. So if I pull with 2 newtons, the force of friction must have been 2 newtons in the opposite direction. If I pull a little less hard, and now I'm only pulling with 1 newton, friction adjusted and now is only 1 newton, again because it did not accelerate. The net force was zero. If I pull harder, up to like 3 newtons, friction adjusted. If I pull with no force, I don't even pull on that thing, the force of friction is zero, which means when you're not pulling on that thing, there's no friction between the block and the table there. If there was friction and I wasn't pulling it, let's say there was a force of friction back off to the left and I wasn't pulling off to the right, well, friction would cause that thing to accelerate off to the left, and that's just, it would be pretty wild to see. So if I don't pull at all, there's no friction. But as I pull harder and harder and harder and harder and harder, friction gets more and more and more, but there was a limit to how much friction there could be. That the most friction could be was this 4 newtons. Let me play that again. We pull harder and harder and harder, friction's getting more and more and more until it got to 4, and then it dropped off to 3 when it was sliding. And that's because this was static. Those peaks and valleys were nestled into each other. But once it started to move, the peaks and valleys were kind of skimming over the top of each other, and we got less friction. So we're going to graph this here. And this was how much friction we got when it was static. This is how much friction we got when it was kinetic, moving. The other thing we had to see is we had an equal sign here, and I'm replacing that now with a less than or equal to, because it wasn't that the force of friction was always 4 newtons. The force of friction was always going to be less than or equal to 4 newtons, because if I don't pull, the force of friction is 0. If I pull with 1, friction's 1. Pull with 2, friction's 2. Pull with 3, friction's 3. But if I pull with more than 4, friction couldn't supply any more. So the force of friction in this case was always less than or equal to 4 newtons. Putting more weight on there, that was the slide where I put all those bags on top of the pallet. But putting more weight presses the wood into the surface more. So this time I might be able to get more than 4. I might go all the way up here to 8 before it breaks free. And then it dropped off to 6. So 8 and 6, I'll graph those here. Stack another 10 newtons on there and pull. They're really pressed together, so I might get all the way up here to 12, and then it drops off to 9 once it's skidding. I'm going to graph those there. It does seem like it's a linear relationship. So this is the maximum amount of static friction. The friction could have been less than that if I pulled with less force, but the most it could have been follows a linear relationship between how hard they're pressed together, that's called the normal force, and then the maximum amount of friction we get. But it looks like the kinetic friction was also a linear relationship, but we just got less friction when it was kinetic. So it looks like the force of friction is proportional to the normal force. If I stood up there, if I removed all those and got my body standing on that, we would have to pull really hard in order for that to be able to slide. So the force of friction is directly proportional to the normal force. When two things are directly proportional, actually I got ahead of myself. Let's say that we're going to do this again, but not have it between wood and the epoxy countertop. Let's have a piece of glass and have glass on epoxy. Do that whole experiment again with various normal forces. We would get less friction for each trial. If I did it glass on ice, with the same normal force, we might get a lot less friction. Or if I did a hard piece of rubber on granite, not real polished granite, but rough granite, you might get a large amount of friction. Each of these lines has a different slope. So if one thing is proportional to the other, you can set those two things equal by finding the number that is the slope between those two. This is the Greek letter mu, and mu is simply the relationship between how much normal force there is pressing the two surfaces together and then that maximum amount of friction. This is called, it's the Greek letter mu, but we use that letter for what's called the coefficient of friction. And these are vectors. The force and the frictional force and the normal force are vector quantities. But if I had a negative force here, that'd be like a force pulling off to the left. It wouldn't result in a negative force here because the force of friction was this way, but the normal force was that way. They're perpendicular to each other, so we really don't even look at the negatives. I'm just putting absolute values around those two because they're not in the same direction. The force of the normal force and the force of friction are not in the same direction. They're perpendicular to each other. Okay, so if we knew the coefficient of friction, we could multiply by the normal force, and that would tell us the maximum amount of friction. So here we have those two graphs. This one, we kept wood on epoxy and looked at when it was static versus when it was kinetic. And this was changing the surfaces. So we actually have two different kinds of coefficients. This is the coefficient of static friction, and this is the coefficient of kinetic friction. So we have different slopes here. That means we would have different slopes here. Okay, so just whatever material there is touching each other, that would determine this number. And then how it behaves when it's static versus how it behaves when it's sliding, kinetic, would give you that number there. So if I pulled on that string with a little bit of force, I get a little bit of friction. Pull with more force, I get more friction. More force, more friction. The harder and harder and harder I pull, the more and more friction I get. But there's a limit to that. There's only a maximum that force of friction could be. Because at that moment it breaks free and it begins to slide, and then now we kind of get an equal amount of friction as it's sliding. Okay, it changed, it grew as we pulled harder and harder, but it broke free and then began to slide. And boy, people have done a lot of work to figure out the coefficient of friction for a variety of different materials. And the Engineering Toolbox is a great website to go to. We could look at brass on steel or car tire on asphalt, if the road is clean and dry or if it's wet. And then we have the static coefficient and the kinetic coefficient. And you need to go to that website to look it up for whatever you need to figure it out for, but there's just a bunch of stuff. So let's say that you have your snowmobiles and you have this big sled, and this big sled is on skis and the skis are waxed. So you could look at the material for waxed skis on snow, and the snow is pretty dry versus wet. This is the coefficient of static friction, and this is the coefficient of kinetic friction. So if this sled gravity's pulling down on the sled really hard, the snow would be pushing back up with 350 pounds. So how hard do we have to pull to get the sled moving? That's when it's static. So this was the normal force. This was the coefficient of static friction. That times that is 35. But I rounded up to 40 because there's only one sig fig in that number. Our answer can only have one sig fig. How hard must they pull to keep the sled moving? Well, once it's sliding, this is the coefficient of friction we use. So that times that, and again I'm rounding to just one sig fig. But you have to pull this hard to get it moving, and this is how hard you have to pull to keep it moving. I guess one thing I should say is that occasionally if it sits there, it can melt the snow and the snow will freeze onto the skis. But that's not a situation that we're talking about here. The coefficient of static friction is always going to be greater than the coefficient of kinetic friction. So that's just what we say there. Coefficient of static friction is always greater than the coefficient of kinetic friction. So let's see if we can apply that to a tire. If a tire is rolling down the road like that, is it static or is it kinetic? A lot of people want to say kinetic, but it's actually static. Even though there was movement, the rubber was not sliding over the surface. It was just touching the surface and lifting off as the tire rolled. If it's skidding like this, tires locked up and skidding, leaving a skid mark there, that would be kinetic friction. And you can easily cross over from static friction when it's rolling, grabbing, and then locking up your tires and skidding. And since the coefficient of static friction is always going to be greater than the coefficient of kinetic friction, you'll always get more friction when it's static versus when it's kinetic. So let's say you're in your car and you're texting or you're tuning the radio station or something, things you shouldn't do when you're driving. You glance up and you notice the car in front of you has stopped, and you can quickly do some mental math and realize you are not going to stop in time, so you have to stop quickly and you yell the F word. Well, that's okay as long as you're thinking about friction. If you think about any other F word, you might be in trouble, unless it's a four-letter F word, spelled this way: physics. If you think about physics or friction, you might be able to stop from hitting that car, which means you can't lock up your brakes. If you start to skid, you'll get less friction and you won't stop in time. Now, I know cars nowadays have anti-lock brakes, but maybe you could apply that to riding a motorcycle or a bicycle or something like that. So just if we press on the brake harder and harder and harder, we get more and more friction, and more friction would stop us quicker. But that's true only up until a point. Once we start to skid, we get less friction and we won't be able to stop as fast. All right, so let's just do some calculations here with this. Let's say we have a brick sitting on wood, and we pull with 13 newtons, and it weighs 15 newtons. And we would like to calculate the coefficient of kinetic friction, because it is going to be sliding, but sliding at a constant velocity. I can solve for this variable by taking the force of friction divided by the normal force. But I want to make sure we see that it's not 13 divided by 15. It's not 13 divided by 15 to give us this. It's when I pull with 13 newtons here, friction pulls back equally, so that the net force was 0 if it's moving at a constant velocity. And if gravity's pulling down with 15, the surface must have been pushing up with 15. So it's not 13 divided by 15, it's 13 divided by 15, if that makes sense. To calculate this, it's not how hard we pull divided by how much it weighs, it's how much friction there is divided by the normal force. And in this case, those two numbers were the same, but it looks like the coefficient of kinetic friction is 0.87. Okay, this is a little bit more complicated example, but I am giving the coefficient of kinetic friction, how much friction there is going to be when it's sliding. So we are assuming that we've pulled hard enough to break free of static friction, and now it is sliding. But we're going to be pulling with 20 newtons at an angle of 18 degrees. It's at an angle this time. And the brick weighs 15 newtons. So we want to calculate the acceleration of this brick. So we're going to use Newton's second law to do it. The sum of the forces divided by the mass of that brick. Well, remember that the force of gravity is mass times acceleration. It's just kind of rearranging Newton's second law. So if I know that the force of gravity is 15 newtons and the acceleration of gravity is 9.8, I could take 15 divided by 9.8 and find its mass of 1.53 kilograms. So I'm going to need to know the mass to find the acceleration, but I need to know the net force. We imagine it's going to be accelerating in this plane, so we have to find the forces in that plane. We were pulling at 20 newtons at an 18-degree angle. So friction is going to be back in this direction, and that's in that plane. But there is also, of this 20 newtons at an 18-degree angle, there is a component parallel to the plane and a component perpendicular to the plane. So the shortcut I've been trying to teach you is that you take the hypotenuse times the cosine of the angle, and it would give us this adjacent side, about 19 newtons, pulling horizontally. And hypotenuse times the sine of the angle would give us this opposite side. There's 6.18 newtons pulling vertically. All right, so we're pulling this way with 19. In the previous problem, we assumed that that friction was pulling back with the same amount, but that's because it was only moving at a constant velocity. It's going to be accelerating this time. So we have to calculate how much friction is pulling back. To calculate how much friction there is, we need to know the coefficient of friction and the normal force. In the previous example, the normal force was the same as what it weighed, but that's not the case in this example. Gravity is pulling down with 15, but this rope here is pulling up with 6.18 newtons. It's lessening how hard the brick is squashed against that surface. So the difference of 15 and this is pulling down, this is pulling up. The difference of that is how hard the surface must be pushing against that brick. So that's the normal force. So if you take the coefficient of kinetic friction times the normal force, this is how much friction there's going to be. So we got friction opposing that motion with 6.17 newtons. Now we're ready to go back and use Newton's second law here, that we've got 19 newtons pulling to the left. We got 6.17 newtons holding it back of friction. That's the sum of the forces that was applied to this mass. It's going to accelerate at 8.04 meters per second squared. The free body diagram for that would be the string pulling here, friction pulling back, gravity pulling down, and the surface pushing back up. This picture I originally showed you, a guy trying to push the tire along, he's kind of pushing at an angle like this. And so as he pushes at an angle like this, there is a component down and a component left. That component down is being added to the weight of the tire, so we get a really big normal force. But that would be a good free body diagram, that as he's trying to push it that way, friction's holding it back, it weighs something, and the normal force is pushing back. All right, now we did this problem when we talked about vector or force vectors, but if I had a 75-pound ball, there's a component this way, there's a component that way. If this is 27 degrees, this is going to be 27 degrees. But if I take the hypotenuse times the sine of the angle, that's how much force is this way. And the hypotenuse times the cosine of the angle, that's how much force is this way. So for him to hold that ball, he just has to push with 34 pounds, even though it weighs 75 pounds. And if you put it on a scale, this is how hard the ball is being pulled against the scale, perpendicular to 67 pounds. All right, so let's just now do this with a box sitting on a slope here. The coefficient of static friction is 0.42, and it's at a 27-degree angle. Is the box going to stay there, or is it going to slide? So doing the same thing we did before, we have 75 pounds pulling down, there's 34 this way, there's 67 that way. So that's the force of gravity, and these are the components. If gravity was pulling against the slope this way, the slope must have been pushing back that way equally. So that's the normal force. We can take the coefficient of static friction times the normal force to calculate how much friction we're going to get. So we're going to get 27 pounds of friction holding it back, but gravity was pulling this way with 34 pounds. There'd be a net force of 7 pounds that way, so it would accelerate that way. All right, let's just do this again. Everything's the same, except this time we have a different package on there, and it has a little bit different coefficient of static friction. So all the numbers are going to be the same, but this time this is different. So we have the most friction could be is 38 pounds this time, holding it back. So if we have gravity pulling down with 34 and friction pulling it back up with 38 pounds, friction is going to accelerate that box right up the ramp. It would be amazing. Well, no, that's not true. Remember that with this less than or equal to sign, that's the most friction could have been. But if friction could have been greater and wasn't, friction is just trying to hold it in place. Gravity was pulling down with 34 pounds, so friction would have been 34 pounds. All right, one last thing here. We're going to put a box on a slope here, and I want to calculate the coefficient of friction between the box and that slope. So you slowly raise it, and find that tipping point where it just begins to slide. So at 28 degrees is where it just began to slide. So we don't have any numbers to work with other than the angle. So the force pulling it down is the mass of that box times gravity. There's a component this way and a component that way. If this is 28 degrees, this is 28 degrees. So we can find the opposite side with sine. We can find the adjacent side with cosine. So this is how hard gravity is pulling against the slope, and the slope is going to be pushing back equally. This is how hard gravity was pulling it along the slope, and we just found the threshold of where friction was just equal to that. Okay, so we can calculate the coefficient of static friction by taking the frictional force minus the normal force, and that's those two numbers. Notice that mass cancels out and gravity cancels out. And I want to solve for this. I got to divide both sides by the cosine of 28. And this is a trig identity we've used a couple times now, but the sine of 28 divided by the cosine of 28 is the same thing as the tangent of 28. So if I just take the tangent of 28 degrees, that's going to give me the coefficient of friction. Now what's interesting about this is that gravity canceled out. Gravity is not a factor on where this thing is going to slide. It's going to slide at 28 degrees, whether it's on the moon or whether it's on Earth. Also, the mass canceled out. It didn't matter if I had just a little package there or a big package there. It's still going to slide at the same angle because mass was not a variable that factored into things. That's a lesson on friction and the math involved in that. It's a little involved, but I think you can handle it.